today's class we're going to kind of talk a little bit about again aspects of settling, but I just want to pose this problem by just saying that say that I have a container and it has particles. Okay, now if I want to and say that these dimensions of these particles are very small. Okay, say that I have the dimensions of these particles, say they're very tiny. Okay, like say sub micron size, say 7 nanometer particle or 15 nanometer particle. When the particles are very small, okay, it so happens that even if you want to use external force, like say we talked about centrifugal force, right? Okay, if of course we know that for smaller size particles, gravity is not good enough to settle the particles down. Okay, however, you can say that look, I'm going to go for centrifugal forces. We know that I can generate, if you look at commercially available centrifuges, you can use like say centrifugal force which is of the order of maybe even 20,000 times g. Okay, it turns out that even such high centrifugal force, it will be very difficult to sediment particles of smaller dimension. Okay, now in such cases what do we do? Okay, because when people work with particulate dispersions, now that there's a lot of interest in going to smaller and smaller sized particles, right, the nano domain. Okay, therefore there comes a case where you're basically interested in looking at separating out such small particles from solution, and it turns out that external forces kind of become not very applicable in such cases. Okay, so what do we do in such cases? So I have smaller size particles. I would like to separate them out or sediment them out from the solution, and I can't use the external forces because the particles are too small. Okay, one way of doing this would be, what is that? Make these particles bigger, right? How do we make the particle bigger? Not the particle bigger, but what I can do is I can actually make the particles large enough. Okay, in terms of what I can do is I can start with this case of homogeneously dispersed particles. I can make them what is called as aggregate, right? Okay, I can make the particles come together so that they form what are called as multi-particle clusters. Okay, also called as aggregates. Now these aggregates, if they are sufficiently big, okay, they could contain many number of particles depending upon the size of the aggregate. And now when the particles become larger in size, we know that I can make use of either gravity or or the other external forces, right? Now how do we go from state A to state B? What do we do? Can you think of some ways by which I have a homogeneous dispersion of particles? I want to go from state A to state B, where I have aggregates of particles. People also call as cluster of particles. People use term called coagulation, flocculation. Okay, these are different terms that you come across in the literature. But I want to go from A to B. So can you think of some ways of doing that? Any thoughts? Should I pick some names? How about Saurabh? Is Saurabh here? Yes, Saurabh. All of you have kind of, I'm sure you kind of looked at this. So basically use additives, right? Okay. Do you know of some process where people use additives to make the particles aggregate or cluster together? You would have heard in the context of water purification, right? People put in what is called as alum, which is aluminum sulfate, which is a salt that is typically added to water to ensure that whatever dirt particle that you have that is there in water, they become larger in size. Okay, and the moment such things are stored in a tank, okay, they slowly settle down, Okay, therefore you basically can obtain water purification, right, or achieve water purification. Okay, so one way of doing this would be additives, right? But it turns out that the kind of additives that you're going to use, it depends on a lot of factors. Okay, it depends on the type of particle that you have in the dispersion. Okay, whether the particles are, say, neutral, or whether the particles are charged. Basically, the characteristics of the particles become important. Okay, and again, what kind of additives you use, that again depends on the particle fluid combination that you're working with. Okay, typically what is done is two types of additives are typically used. One is basically adding a salt. Okay, I gave this example of alum, right, which is an aluminum sulfate, which is a salt that is added in the water purification. And other kind of additive that people typically use is a polymer. Okay, and the way the salt helps in the aggregation and the way the polymer helps in the aggregation, the mechanism is very different. Okay, but the take home is that you have a dispersion of particles, very tiny particles in size, very tiny particles, and I would like to make them larger. That means I want to cluster them to make a multi-particle aggregate, and you can use additives. You can either do that by adding salt or by polymers. Of course, there are a lot of other additives as well which people use, but for today's class we'll just stick to these two. Now, I've added an additive. How does it work? Okay, so the way all these additives work is that it basically alters. Okay, it basically changes what is called as interparticle interactions. Okay, in terms of we talked about this intermolecular interactions, right? Okay, where we talked about Leonard-Jones potential, which has a repulsive part and an attractive part. Okay, and that's a plot of how the potential varies as a function of separation. This is what I was mentioning in the tutorial, that you have to work with dimensions which are sub-nanometer. Otherwise, any distance larger than a nanometer, you're at least for the Leonard-Jones potential, your potential of interaction is 0. That means essentially the molecules are non-interacting, right? So there's a repulsive part, there's an attractive part, and that's the overall potential. That's the total potential here, and there's a minima, and basically I can get that by just differentiating this equation and equating to 0, right? And it turns out that the minimum occurs at that's a minimum position, and that's a energy corresponding to the minimum, right? So similar to intermolecular forces, you can also play with interparticle forces as well. Okay, when you talk about particles in a solution. So I'm just going to flash a slide where we're talking about, in this case we're talking about colloidal interaction. That means interaction between the particles in the case of charged particles in a solution. Okay, analogous to the Leonard-Jones potential. So the total potential, okay, phi dLVO is what is called as the total potential, and dLVO actually stands for the 4 scientists who basically came up with this formalism, that the total potential in the case of a charge stabilized dispersion, that means a dispersion which contains charged particles, it basically has the van der Waals contribution and a electrostatic contribution. Okay, and this dLVO stands for the name of the 4 scientists, Derjagun, Landau, Verwey, and Overbeek. Okay, these are because these are two groups of 2 scientists, one from Russia, one from Netherlands, which came up with this argument. Okay, and like the Leonard-Jones potential, there's a attractive part which is the van der Waals. That's the one that is in the the below that 0 axis, right? And there's a electrostatic repulsion term. Okay, and that's the total potential. Okay, right? Now, I don't want you guys to know a lot of details about this, but the point that I want to make is there is a van der Waals term. Okay, the van der Waals force of attraction. It depends on a parameter A, which is what is called the Hamaker constant. Okay, what is called as a Hamaker Hamaker constant. Okay, this basically contains all the material properties of the particle that you're dealing with. Okay, this takes a certain value for, say, polymeric particles, certain value for metal oxide particles, certain value for metal particles and stuff like that. Okay, and this D is the separation distance. Okay, so it depends on the kind of particle that you're working with. okay, and it depends on the separation distance between the particles. Okay, that's the van der Waals term. And the electrostatic term, okay, it depends on a parameter called kappa, okay, and that kappa depends on the salt concentration that people are working with. Okay, I have a dispersion and I've added certain amount of salt. I know the concentration of the salt that I'm working with. Okay, it only depends on the salt concentration. It depends on the valency of the ion that I'm using. I mean, whether I'm using a sodium chloride, that is Na plus and Cl minus, or whether I'm using a CaCl2, right, Ca2 plus and 2 times Cl minus, right. So it depends on the valency of the ions that I'm working with, and of course it depends on the thermal energy kBT. It depends on the permittivity, right, of the medium in which the particles are dispersed. Na is the Avogadro number, E is the charge that the electron has, right, the elementary charge. Okay. Plus there's a term called capital gamma square, which basically depends on the surface charge of the particle. Okay, whether the particle is highly charged or less charged, okay, it depends on something like that. Okay, so what people do is there's a lot of work that has gone on in in looking at charge stabilized dispersions and their interactions, and people have come up with a way of manipulating the interaction between the particles. Okay, either I can make the the attractive forces more, or I can make the repulsive forces more, okay, depending upon whether I want to have a stable dispersion. What I mean by that is whether I want to have a state like this or I want to have a state like this, I can manipulate this by changing the interactions. Okay, that's the point. Okay, and just to give you a little bit about whenever I have so what you're looking at is a schematic. Okay, what you have in the inner, that's a charged particle. Okay, in this case the particles are positively charged. Okay, and the moment you have the moment I put in a particle in water, okay, and if it acquires charges, okay, and one of the ways of acquiring charges could be, say that I have, like, say a particle which has, say, COOH groups on the surface. Okay, the moment I put this in water, what happens is that it is going to dissociate and it's going to give a particle that is negatively charged. Similarly, I'm going to have 3 H plus ions, right? That's the what I call as a counter ions. Okay, now that's a positively charged particle, and these are the negatively charged counter ions. Okay, and because of the fact that I have a positively charged particle, and if there are negatively charged ions in the solution, the electric field that is developed because of the positive charges on the particle surface is going to attract the negative charges, right? Because of which there is going to be a concentration of negatively counter ions, or the negatively charged particle in this case, close to the particle surface. Okay, so in a way I have a picture of what is called as a charge that belongs to the particle surface and a charge that is in the solution. Okay, this is what is called as the electrical double layer. Okay, okay, that is the charges on the particle surface that constitute one type of charged surface. Okay, and there's a charged surface that is surrounding the particle, and this kind of combination is what's called the electrical double layer. I just want to introduce the terminology. Okay, this phi electrostatic, okay, it's also called as phi electrical double layer because of the fact that the moment you have a charged particle in solution, the configuration around the particle looks something like this. Okay, and this is the K that I was talking about. This K, if you work out the units of K, it turns out that K has a units of meter inverse. Okay, and therefore this K inverse will have a unit of meter. Okay, this K inverse tell you something about the length scale, okay, up to which I have to worry about the electrical double layer interactions. Okay, I talked about the range of interactions, right? In the case of Lennard-Jones, I said that any distance greater than 1 nanometer, I don't have to worry about the interactions because beyond that the interactions are not present. Okay, in essentially, right? In the case of charge stabilized dispersion, if the particles are such that the distance between the particles is more than K inverse, okay, then I can practically neglect all the electrical double layer interactions or the electrostatic interactions because Now the particles are far enough that the repulsive interactions don't come into picture at all. Okay. However, the van der Waals force of attraction typically occurs in the size range of in the length scale of the order of a few nanometers up to about 10 nanometers. Okay, that's the distance. Okay. Now what I can do is, I know a little bit about van der Waals. It depends on the type of the particle that you're working with. I know a little bit about the electrical double layer interaction. It depends on the kind of salt that I'm using. It depends on the concentration of the salt that I'm using. Also the charge on the particle. What I can do is, I can actually play with the double layer interactions. Okay, this is a case where what is being done is, this is your phi net, that's a total potential plotted as a function of distance. Okay, what is being changed is the Hammacher constant. Okay, what I mean by that is, your phi dlvo has phi van der Waals plus phi electrical double layer. What is being done is, your phi electrical double layer is basically kept constant. Okay, the only thing that you are changing is the van der Waals force of attraction. Okay, and that I can actually change by changing A, right, the Hammacher constant. Okay, if I increase the Hammacher constant, okay, if I increase the Hammacher constant, you can think about this barrier. Okay, this barrier as a energy barrier. Okay, for aggregation. Okay, that means if the total interaction potential is negative, okay, that means if I somehow ensure that the particles do not come to a distance which is smaller than the distance that is corresponding to this vertical line, right, any distance that is less than this, if I ensure that the particles do not come to such sufficiently small distances, the particle would continue to remain in a well dispersed state, right. Okay, and for them to come to the such close separation where the attraction becomes dominant, that means what I have to do is, I should ensure that the separation between the particles never occurs. What I mean by that is that I should ensure that the separation is sufficiently large that this energy barrier is kind of prominent, that the aggregation does not occur. Okay. Okay, the point is that look at the energy barrier. Okay, the energy barrier is this in the case of 2.2 10 power minus 20 J Hammacher constant. I have reduced the Hammacher constant now it becomes a little smaller. I have reduced the Hammacher constant further, or sorry, I have increased the Hammacher constant further. Okay, basically I am playing with this barrier, right. I am basically reducing the barrier by increasing the Hammacher constant, and what that leads to is at some point your interaction become completely attractive. Okay, therefore, if you keep the van der Waals force of, so if you keep the electrical double layer interactions same, if I play with the van der Waals force of attraction, okay, I can actually go from a nicely dispersed state, which is what is you would have if your Hammacher constant is lower, 2 into 10 power minus 20. Okay, however, if I go on increasing the Hammacher constant, that is if I go to A into 10 power, A is equal to 2 into 10 power minus 19, I have just reduced the Hammacher constant by 1 order of magnitude. Your interaction becomes completely attractive. That means I am going from a well dispersed state to an aggregated state just by changing the van der Waals force of attraction. Okay, any questions you have? Okay, the point to note is that there is an energy barrier for aggregation. Okay, and that energy barrier occurs at sufficiently close distances, right. If you look at this, right, if I look at this plot, so I would say that the energy barrier maximum is about 1 nanometer, right. It occurs at 1 nanometer. That means if I somehow ensure that the particles approach a distance that is less than 1 nanometer, that means I am already crossing the energy barrier. Okay, then the particles are going to cluster together and they're going to make aggregate, right. And one way of changing this energy barrier is basically I use particles of different types. Therefore, I am basically increasing the Hammacher constant, going from 2 into 10 power minus 22 2 into 10 power minus 19. Okay, that leads to the totally attractive interactions, and your particles would become unstable and aggregation kicks in. Okay. Second way of doing this would be if I work with particles of different charges. Okay, I don't want to get into the details, but the charge is basically measured in something called as a surface charge is basically measured in terms of what is called as a surface potential. The only thing that is important at this point is A higher value of psi means higher charge. Okay, that's the only thing that's important at this point. Okay, and what I'm doing is I'm basically decreasing the surface charge, or I'm decreasing the surface potential. Okay, going from 231 all the way up to 103. Okay, and you can clearly see that if this is a barrier to begin with, okay, I'm basically reducing the barrier by changing the surface potential, right? Again, this is another way of making sure that the aggregation occurs. That means if I want to go from a well dispersed state to an aggregated state, second way of doing this would be playing with the surface potential or the surface charge. Okay. So in this case, what is done is you have basically kept the phi dlVO is van der Waals plus phi electrical double layer. I've kept phi van der Waals same. Okay, your Hamilton constant is kept constant. Your Hamilton constant is kept constant at 2 into 10 power minus 19 joules. Okay, and you kept the salt concentration same. As I said, the salt can also influence the potential. I've kept that also same. The only thing that has changed is the surface potential, and that's how you're basically manipulating your electrical double layer interaction. Okay, and the third way of doing this would be by the addition of salt. Okay, which is what I said is most commonly followed in practice. That again, this is the energy barrier. Okay, with certain salt corresponds to certain value of kappa. Okay, and by increasing the salt concentration, I am basically reducing the barrier. At some point, your electrostatic potential becomes completely, the total potential completely, becomes attractive. That's because again here my phi van der Waals is kept constant. I am basically reducing the electrical double layer interactions. Okay, I am reducing it by changing the salt concentration. Okay. So therefore, whenever you are working with a particle that have charge, I can play with the material properties, or I can play with additives such as salt, right, and manipulate the total interaction so that your overall interaction goes from a purely repulsive, so a case like this, to an attractive, so that I basically induce the clustering of particles, right. Now, other ways of doing this would be by putting other additives, polymer for example. Okay, again the use of polymers as additives to tune the interaction between the particles is again a big field. There's a lot of literature. If you're interested, I can go through it, but I just want to give you a feel for a particular term called bridging flocculation. So what could happen is, if I have particles in a dispersion, I add in a little bit of polymer, and if this polymer has a tendency to go and adsorb onto one of the particle surface, if this is a particle 1 and if this is a particle 2, okay, if it goes and adsorbed onto the particle surface, and if another particle comes in its vicinity, okay, it will also can adsorb onto the other particle as well, right. So therefore, this polymer kind of bridges, okay, the polymer bridges the two particles, and now if many such particles come into picture, for example, I could be one more here, okay, therefore I can again make a particle cluster. In this case, the clustering of particles is basically done by adding a polymer that goes and adsorbs onto the particle surface, and when many particles come together, so you basically get a multi-particle cluster, which is basically held together because of the additives that I've added. Okay. Now, okay, so these are a couple of different ways of doing it. I mean, again, there are different mechanisms of how the polymer addition helps in aggregation, so that we'll not talk